Section 3.1 is inequalities and their graphs. I can write, graph, and identify solutions of inequalities. Big ideas. An inequality is a mathematical sentence that uses an inequality symbol to compare the values of two expressions. Inequalities can be represented with symbols, and the solution of an inequality can be represented on a number line. So in example 1 here, we want to know what inequality represents the verbal expression. All real numbers x less than or equal to -7. 6 less than a number k. Here, since it's specifically 6 less than that number, we subtract. Less than a number k, remember, is k minus the 6, because it has that than as comparison. Now that whole quantity that we don't know, so 6 less than a number k, 6 is an exact amount. We can write that as subtraction. But k minus 6 is not an exact amount, so is greater than is our inequality. And 13. Again, here we want an inequality that represents the verbal expression. Inequalities are less than, greater than, less than or equal to, greater than or equal to. So, all real numbers p greater than or equal to 1.5. Remember, the alligator's hungry. It always wants to eat the bigger number. Greater than opens up towards the bigger thing. The sum means we're going to add of t and 7 is less than -3. A solution of an inequality is any number that makes the inequality true. So here we want to know if -3 is a solution. So I take my inequality, 2 times x plus 1 is greater than -3. And I check my x value of -3 by substituting it in. We simplify, multiply first, then we add or subtract. Now my left side is as simple as we can get it, and so is my right side, so we check. Is -5 greater than -3? The answer here is no, it's not. So, is this a solution? No, because this is false. Now let's check -1. Same idea. I'm going to take my inequality, 2 times x plus 1 is greater than -3. And I'm going to plug in my value, -1. My left side's not as simple as I can get it. According to PEMDAS, we multiply first. Then we add or subtract. And now both sides are as simple as I can get them, and I check. Is this true? Is -1 greater than -3? Yes, it is. So is this a solution? Yes, because this is a true statement. Now let's take a look at the graphs on the bottom of page 165. I have them here as well. The first inequality is n is less than 1, and that's a less than symbol. So at 1, we put an open circle because it's not equal to. If it's equal to, okay, it's one of our answers, and all of our answers are shaded. Our boundary point is what we call that one. That's where it splits our graph into everything that is an answer to everything that's not. Sometimes that's included. When it is, we fill it in. When it's not, we leave it open. We want numbers less than 1, like 0. So we shade all along this side, including the arrow, to tell us it goes on forever. A is greater than or equal to 0. Okay, this is a greater than or equal to, which means my circle is still at that boundary point, but here I fill it in because it's got this cute little equal to line. Since my equal to part is filled in my inequality, my circle is filled in to show equality as well. And we want numbers greater than 0, like 1. So we shade this way. Again, including that arrow. F is greater than -3, so at -3 is my circle. It's not filled in because it's not equal to. Remember, we only shade things that are equal to, that are part of our solution. We want numbers greater than -3, like 0. So we shade everything on that side because, again, our boundary point, that -3, splits our graph. Everything on one side is not a solution. Everything else is a solution. So if one of the numbers is a solution, everything on that side is a solution. In here, this is a greater than symbol. So -2 is my boundary point. It's equal to, so we fill it in, and we want -2 to be bigger than our numbers. -2 is greater than -3, for example. So we shade everything on the side with -3. We can also reverse that last inequality if we wanted to, as long as the alligator keeps eating the same thing and we're pointing at the right thing. So alligator's eating -2, alligator's eating -2, we're pointing at x, we're pointing at x. It's the same relationship, it's just written backwards. In example 3 here, we want to know what is the graph of 2 is greater than or equal to a. Well, remember, our variables are all of our answers, all of our possibilities. That's our shading. So on my number line, I'm going to put my boundary point 2. I always want you to have the next number bigger and the next number smaller. I also always want you to have 0. And you don't have to count to 0 here. It fits nicely. It doesn't always. So just to put 0 on whichever side of our numbers it should be. Okay, so it doesn't have to be to scale. We're going to put a circle at our boundary point, 2. Now we look at our inequality. It's equal to, so I filled that part in. And then we want 2 to be greater than our numbers. 2 is greater than 0, for example, or 1, or anything negative. So we shade everything on the side of our graph that has a solution. Because again, that boundary point splits it into everything that is a solution compared to everything that is not. Now, feel free to pause here and give this a try if you'd like. We want the graph of the inequality. So I'm going to start off with a line for my number line. I'm going to put my boundary point on it. I want the next number bigger, -3. The next number smaller, -5. I also want to make sure that I have 0 on there, which is over here somewhere. It's not necessarily to scale. I don't need every number to it, but I need to know that 0 is off to the right there. I put a circle at my boundary point, and I look at my inequality. Here it's not equal to, so I don't fill it in. Okay, I leave it as an open circle. And then we want numbers that are greater than -4, like -3 and 0 and anything positive. So we shade everything on the side that has our solutions. In B, I put my number line. My boundary point goes in the middle. Put the next number bigger, the next number smaller, and here I already have 0, so I don't have to worry about that. I look, circle at my boundary point. It's not equal to, so I don't fill in that circle. And then we want numbers less than 0, like -1 and anything else negative. And so we shade everything to the left. Let's try C here. I put 3 as my boundary point. I put the next number bigger, the next number smaller, and I make sure I have 0. And the reason we do that is those are our test points. Those help us figure out which way we need to shade. I look at circle at my boundary point. I look at my inequality here. It's equal to, so I fill in my circle. Since the equal to line is filled in on my inequality, I fill it in on my graph as well. Now, we want 3 to be less than our numbers. So 3 is less than 4 and 5 and 100, anything bigger. So we shade everything on the same side as our solution of 4 there as our test point. In example 4, we're going to work backwards. We're going to write an inequality from a graph. So in A, I'm going to start off with all real numbers x. Then I look at my inequality. I have a boundary point at -1. It's filled in, so I know my inequality is going to be equal to, and I have numbers that are greater than -1. 0 is greater than -1. 1 is greater than -1. 2 is greater than -1. So all real numbers that are greater than or equal to -1. In B, I'm going to start off with all real numbers, x. I'm comparing them to my boundary point of 4. Here my circle is open, so it's not equal to, but I have numbers like 3, 2, 1, 0. All those numbers are less than 4. So my inequality is a less than. Here's a little spoiler alert, guys. As long as you list your variable first, like here I have x first and x first, our inequality symbol is going to match our arrow. Here I have a less than, it matches my left arrow. Here I have a greater than, it matches my right arrow. So just something to keep in mind. But again, that only works if your inequality is listed, or if your variable is listed first. Now feel free to pause here and give this a try. For A, I have all real numbers, x. My boundary point is -3. If I look at my circle, it's an open circle, which means it's not equal to. And my shading are numbers that are less than -3, like -4, -5, more negative numbers. So here x is less than -3. In B, I have all real numbers, x. My boundary point is at 0. If I look at my graph, it is filled in at that circle, which means my inequality is equal to. And then I look at my numbers. My answers are 1, 2, 3, and 4. And in relationship to 0, 1 is greater than 0. 2 is greater than 0. 3 is greater than 0. So x is greater than or equal to 0. Here, in example 5, we're doing real-world inequalities. What inequality describes the situations displayed on page 167? I have them here. Make sure to define a variable. So in A, we are talking about trail rides. So the cost starts at $19.99. So I'm going to make C my cost of the trail ride. That's my variable. That's the part that changes. So C, my boundary point is $19.99. That's what splits my costs into things I can have to things I can't. Here, since they start there, it means it could be equal to. And since it starts there, it means that that's the smallest it could be. It could be $30. It could be $70, depending on what you add, possibly. So my cost could be greater than or equal to $19.99. Here, again, I'm going to make speed my variable because we're talking about miles per hour. So speed. Our speed boundary point is 8. That's what splits everything into okay versus not okay. It could be equal to, that's our limit. And here, if our speed limit is 8 miles per hour, okay, that's the highest we can go, which means we could go 5, but we can't go 10. So here it's less than or equal to 8. On page 167, there's a concept summary to take note. It has our inequalities in words, x is less than 3, in symbols, and as a graph. Greater than or equal to, or less than or equal to. So this is a good place to look back. Again, page 167 if you need to, if you're confused on anything. And a quick recap here. An inequality is a mathematical sentence that uses an inequality symbol to compare values of two expressions. Inequalities can be represented with symbols, and the solution of an inequality can be represented on a number line. And that's all I have for section 3.1.